So hello everyone, I am Pavan. I am an expert on Codeforces 1800 rated. Today I'll be going to tell you about binary exponentiation, a very easy and important algorithm. So what is binary exponentiation exactly? Many people may know it as an efficient way to calculate a power b or something like this, right? Which is right. But there are a few more applications to it. Let's discuss all of them. Today we'll be discussing obviously this one and also something else which is known as modular exponentiation, which is nothing but binary exponentiation uh, uh, along with some modular operation so that the large numbers always remain in a particular range. They never exceed the range of that particular modular. So it's also it's very basic. This one's also very basic, and there are a few more applications. We'll be solving a few questions, and also we'll be learning something about matrix exponentiation, matrix exponentiation, and also we'll be knowing how to calculate Fibonacci of n using matrix exponentiation. The approach most of you may know is the recursive approach, either the recursive approach, which is uh, the famous Fibonacci recurrence relation f of n equal to f of n minus 1 plus f of n minus 2, or the DP approach. This would take O of 2 power n, O of 2 power n, and you may also know the DP approach, which would take you O of n, but this matrix exponentiation would take you O of log n, so it's very efficient. Let's know how we'll be doing this. Okay, so these are all the things we'll be knowing today. Fine. Uh, Please don't forget to subscribe and share this video so that I can bring you more content. Okay, coming back to the topic, binary exponentiation. So the first application. Before that, let's discuss what exactly is binary exponentiation. So it's a standard way of dealing with any functions. Let's call the function f. If f is associative, if f is associative, which means let's say multiplication. Multiplication is associative, right? X into y into z is equal to x into y into z. This is what we call associative. So whenever the properties are related to this, we can use this concept of binary exponentiation. When you are asked to calculate any f power k of some arguments. Arguments are not necessary here, it could be anything. But if f is associative and you are asked to calculate f of k here, in that case, well, f of k means uh, f of so until like k f's. This is the, let's say this is f1 time, this is f2 times, f3 times, fk times. If this is the case, if you are asked to calculate this, then you'll use something known as binary exponentiation. Okay, so coming to the first thing, the basic application, which is a power b. Let me write it neatly, a power b. So how is this gonna work? How is this gonna work? Usually a power b, the calculation takes a into so until b times, right, so until b times, it takes so until b times, so it's o of b. You're multiplying a b times, so it's o of b. And if b is a very large value, uh, the power function also uses this. So if b is a very large value, this cannot be applied, power function cannot be applied. In that case, we use something known as binary exponentiation. So let us see how it works. Let's say we have some 2 power 6. All right, we have some 2 power 6, which is equal to 64. We know it's 64. But how to compute this using binary exponentiation? Very simple. Let's take this 2 power 6. Since 6, normally what you need to do, you need to multiply 2 6 times. So 6 times, see, we are dealing with a computer, right? So if you give it 2 or any large number, would the space complexity or time complexity somehow increase? Like we know it takes some 4 bytes, right? If you give 10, would it take less space, and 1000 if you give it, will it take more space? No, right? For 10 and 1000, it would take the same space. All right. So for 10,000, 10,000, 10,000, 1 lakh, whatever you give, it would take the same space. So the base doesn't really matter. The base doesn't really matter. All that matters is the power. If even it's 10,000 power 6, it would be 10,000 getting multiplied 6 times. So the computations would still remain same. So what am I saying is, if we need to optimize somewhere, we need to optimize on the power itself. All right, we need to optimize on the power itself. So now currently we are multiplying 2 6 times, right? Can we somehow reduce this? Yes, we can. Since 6 is an even number, we can do something like, we can convert this to, this can be rewritten as 4 power 3. Alright, this can be rewritten as 4 power 3. What did I do? I used the basic exponent property, that is, if you divide it by 2 and if you square this, it would be the same, right? I can write this as 2 power 2 into 3. So now I can do something like 2 power 2 power 2 whole power 3. I can do this. Alright, okay. So this is an associative function, the power. Alright, so we can do this basically. Now, can I reduce this further? Can I reduce this further? Yeah, I can write it as, I can do this only when there's even powers. I can reduce it only when there's even powers. So how about creating some even powers? How about creating some even powers? So if I do something like 4 square multiplied by 4, alright, if I do 4 square multiplied by 4, now I have an even power. Now I have an even power here. 2 is an even power. That means I can rewrite this as, 16, which is 4 square, and 2 divided by 1 is 1. Now, I have this multiplied by 4. 16 into 4 is equal to 64. I've reduced it to this extent. So now this takes any intuition of any basic algorithm here. Do you know some algorithm which reduces a space by dividing it into half, then again dividing it into another half, then again dividing, so on. Okay, do you know any such algorithm? There's one such algorithm known as binary search, right? Binary search, which takes O of log n, So this also works in the same way. The same binary search derivation would be there for this one too, right? So this also has the time complexity of O of log n. So now you can compute powers. With O of log n, time complexity. So let's write code for this. Okay, let me define int long and name, and let me take some inputs a. All right, this is what we need. Yeah, this is what we need, right? A power b. So let me write a power function. So now, if b equal to 0, b shouldn't be equal to 0, right? No use of it. Let me take a result variable, which would store my final answer. All right. Now, if my b, which is the power, if it's odd, this is a way to check odd. If it's an odd number, the least significant bit would be 1. So if you do ampersand 1, which is and 1, bitwise and operation, you would get 1. 1 and 1 is 1. Okay, true and true. It's true, right? So you would get odd. And if it's odd, you would multiply base to this. Let me write it clearly. You would multiply base to this, so that this this part you are already multiplying to something known as result. So now you need not consider it here. Result already has 4 here. Fine. Result already has 4 here. Okay. Now, otherwise, if now, however, you have countered the odd case, now all you need to think about is the even case. Even in odd case also, we'll be doing base equal to base into base, and sorry, we haven't called it base. Let me call it a once again. So you would square the base and exponent is divided by 2. Okay, exponent is divided by 2. You can write it as, okay, you can write it as like this, or else you can better write it as this. All right, this is what you get. All right, now let's take some inputs. Let's take 2. 2 is the base, 6 is the exponent. This should print 64, right? It prints 1. Sorry, b is greater than 0. My bad. Yeah, 64. Okay, that was a negative aura movement, but fine. That was a silly mistake. Okay, now coming to the second thing. I hope this is clear. Once again, if you want, I can explain this, how this thing actually works. So let me once again take the example of 2 power 6. So you have 2 power 6. In code, you cannot actually do these kind of things, right? Writing a number beside this, you cannot actually do this in code. So you need to store it somewhere. So we are using a result variable. We are using a result variable. So result is initially 1. Now you have 2 power 6. So this is an even power. When it's an even power, what you do? You do base square and exponent divided by 2. So you have 4 power 3. Result won't be affected. Alright, result won't be affected. Now, second step comes. Now it's odd power. Now what you do? Now what you do? Take write this as 4 square into 4. 4 square into 4. Since you cannot write this in code, you cannot write like this. You would update it here. Alright. And 4 square. Now once again you have an even power. When you have an even power, what should you do? When you have an even power, you should do this divided by 1 and base square. So now it becomes 16 power 1. 1 is again an odd power. 1 is again an odd power. So what you do? You multiply this with result here. Alright, you multiply this with result. Result becomes 16 into 4, which is into 4. Sorry, result becomes 4 into 16, which is equal to 64. Fine, done. So this was binary exponentiation. Now let's talk about some bigger numbers. What if it's some 10 power 6 or something like that? Okay, it exceeds the capability of long. Then what you do? You use something known as modular exponentiation. Or else if the question asks you, since the numbers or the answers could be very large, return it in modulo 10 power 9 plus 7 or something like that. If the question demands this, you use something known as modular exponentiation. What is modular exponentiation? Very simple. Whenever you perform an operation, just use a modular. Let me take 1e9 plus 7. Okay. Whenever you're multiplying stuff, just use this modulo. Then this becomes modular exponentiation. Alright. And a itself could be very large. So let's take a equal to a modulo mod. Fine. Okay. A itself also can be very large. Like directly it could be very large. So always prefer doing this. That's it. That's what you call modular exponentiation. It would print once again the same thing. Since 2 is a small number, it would print the same thing. So it's printing the same thing. So far we are done with binary exponentiation and modular exponentiation. Now let's talk about one interesting application. Of this binary exponentiation. How many of you know that? Permutation is associative. Okay, permutation is associative, by the way. Let me tell you if you don't know. So this permutation stuff is associative. What's a permutation? If you are asked to calculate some 10, 20, 30, this is, let's say, a sequence S, and let's say 2, 0, 1. This is a permutation which you're asked to calculate. Now S dash is, let's take S dash. What is S dash? S dash is applying this P permutation to S. So what is S dash exactly? So it's S of 2, S of 2, S of 0, S of 1. So this is S dash. The S dash means applying permutation P to S. So this becomes, what is S of 2? S of 2 is 30. S of 2 is 30. S of 0 is 10. S of 1 is 20. Is that clear? This is 0, 1, 2, right? 0, 1, 2. Alright, this is 0, 1, 2. Now, what is S double dash? S double dash is S dash 2, S dash 0, S dash 1. So S double dash becomes S double dash becomes what is 2, 20, 30, 10. I hope this is clear. So we need to, let's say, calculate S kth dash. So until, let's say, k dashes are there, what would you do? So I've already told you permutation is associative. Permutation is associative. So can we apply binary exponentiation to this? Can we apply binary exponentiation to this? Yes, we can. Yes, we can. Okay, so it's always a good habit to use long. Whenever you are using long, either use int 32t or sign main, because long main is not sensible to the compiler. So let's say you have a vector in sequence and of length, let's say 3, the same sequence which we took. And permutations should also be of the, let's call it S only. Permutations should also be of the same length, 3. Let's write it here only. Why to again take an input? 10, 20, 30. Alright, 201. Now we need to calculate kth permutation, right? So let me just do cout kth permutation of S, P, and let's take input as k. Alright. Alright, so this is the kth permutation method. Let's write a separate method for permuting. Okay, let's write a separate method for permuting or applying permutation. Let's call it permute. Okay, let's call it permute. This will take, okay, this will take these arguments. This should also take k. Okay, so we have a permute function. What does permute do? What did we do here exactly? Let's create a new sequence. Let's call it ns. Ns equal to s dot size. Okay. New sequence should also be of the same size, obviously, because it's a permutation. So now, okay, so now what should we do? Let's iterate over p. New sequence of I is equal to s of p of I, right? The previous sequence permutation. This is what we need to write. Perfect. That's it, right? The apply permutation function. That's what it does. It takes p of I and new sequence is equal to s of p of I. Now coming to the kth permutation. Since we know that it's an associative operation, we can apply binary exponentiation. See, if permutation is, let's say, a function, the permute function, let's call it f. Okay, let's call it f. Applying permutation k times would mean f power k, right? F power k. All right, applying permutation k times. So it's exactly what binary exponentiation does. It calculates power of a function. Like if a function is associative function is applied, let's say m times, binary exponentiation is used to calculate that. We know it. So let's apply it. Okay. We have a standard template. K is less than 0. K is the power. If K ampersand 1, then something. Then what? Let's take a... Okay, this should be a vector int, right? Res once again. Okay, we have a vector int res. If this is we need to apply kth permutation to the s itself, so let's take it s. All right, let's take it s. So res equal to, if k is odd, res equal to permute. Okay, we need to reduce the power by 1. We need to reduce the power by 1. That means we need to permute sequence with p one time, just one time. Otherwise, we need to permute the permutation itself. Otherwise, we need to permute the permutation itself. Okay, with itself, permutation with itself, and you can reduce k's power by... Okay, you can divide k by 2. Finally, return result. Actually, we don't need this extra variable. Sequence is doing the same thing, so we don't actually need the extra variable here. Did we miss something? Why are we getting an error squiggle here? Let's run this once to see if there are any errors. Let's calculate. We have already calculated like second permutation. So let's calculate the second permutation. Okay, this returns a vector int, so that might be a problem. Let's print it. Got an error. Let's see what happened. We should have written S here. Expected something before this. Now don't tell me this is wrong. Okay, whatever, let's run it again. Once again an error, small errors. Return sequence, right? Return sequence. Yeah, 10, 20, 30. That's what it's printing. Okay, it shouldn't be printing 10, 20, 30. Let's reduce this by 1. Okay, once again the same mistake. Done. Yeah, 20, 30, 10. That's what it should be printing. Okay, let's write this mistake somewhere so that next time we don't miss this thing. I'm very sorry for it. Fine. Now coming to the interesting part, which is uh, matrix exponentiation. Matrix exponentiation. Once again, matrix multiplication. Let's take two matrices. Let's take two matrices. Is matrix multiplication associative? Is matrix multiplication associative? Yes, it is. If you take three matrices, let's say A multiplied by B multiplied by C, it's equal to A multiplied by B multiplied by C. So it is. Is it? No, right? This is not always true, but the exponentiation part is true. Matrix can be exponentiated. This is only true when A, B, and C are equal. All right. This is only true when A, B and C are equal. Alright. So this is matrix exponentiation. We can write it, right? We can write it, obviously. If someone asks you, find A power K, it's pretty simple for you, right? You can apply, you can write a multiply method maybe. You can apply multiplication by multiply method. Write a method multiply. Ideally, it's for 4 cross 4. Sorry, 2 cross 2. 2 cross 2, like 4 elements. Okay. Ideally, it's for 2 cross 2. Most often, you'll be countering the cases when you have 2 cross 2 matrices. But you can apply it for higher order matrices also. If you modify multiply function a bit, I would be telling you for 2 cross 2 only for now. You can extend it to some 3 cross 3, 4 cross 4, anything. Alright. So for simplicity, also you can use a matrix. Let's discuss Fibonacci of n using matrix exponentiation. It would be great. Okay. We can also learn matrix exponentiation and the Fibonacci part at a time. So what Fibonacci what Fibonacci says is, let's say you have something. You have this matrix 1 1 1 1 1 0. Let's say you have this matrix. This is the special matrix which we use for Fibonacci. Why is this special? Here this is f of, what is this? F of n minus 2. Sorry, f of 0, f of 1, f of 1, f of 2. Okay, so this is the special matrix which we use, which is 1 1 1 0. This is the special matrix we use for Fibonacci. When you do this, n minus, when you apply power n minus 1 to this becomes, when you apply the power n minus 1 to this becomes f of n, f of n minus 1, f of n minus 2, sorry, f of n minus 1, f of n minus 2. Alright, when you apply power n minus 1 to this becomes f of n, f of n minus 1, f of n minus 1, f of n minus 2. Alright, very clear. So let's code the Fibonacci itself using matrix exponentiation. Let's don't forget that greater than this time. Okay, my aura is already minus infinity by now. Okay, why is this showing an error here? I know this is right. Okay, let's see later. So since we know it's always going to be a matrix with 4 elements, does it make any sense to actually I can say taking an actual matrix like a 2 cross 2 actual matrix? No, right? You can also take an simple array. A simple array you can take, and this would represent a what was it called in high school? Yeah, a11, a22, sorry, a11, a12, a21, a22. You can do this, right? So let's take a struct matrix maybe, or else you can understand by an array. Let's take a struct matrix. This would be better. Let's have int a, b, c, d. Okay, this represents, let me draw it for you. Okay, competitive programmer to ASCII artist. Let's see the transition. A, B, C, D. So this is it. Okay. When we mean, what we mean is, when you write this struct matrix A, B, C, D, this is what we mean actually. All right. Now let's write function to multiply matrices. Let's call it, it would return a matrix obviously. Matrix MUL. Matrix MUL. It would take 2 matrices. Let's take matrix ampersand X and matrix ampersand Y. Okay, if there are 2 matrices, how do you multiply them? or else let's call it multiply, the full name sounds better. If let's say this is, let's take two matrices, 2 cross 2 matrices. Let's call it XA, XB, XC, XD, and let's call this thing as YA, YB, YC, YD. So we need to do XA, YA, XA, YA plus XB, YC this way, and this would be equal to XA, YB plus XB, YD. This would be equal to XCYA plus uh, XCYA plus XDYC, and finally this would be equal to XCYB plus XDYD. Fine. Now let's write the same thing here. We would have a resultant matrix RES. Okay, we would be having this matrix RES. So RES A, resultant of A is equal to XA multiplied by YA plus, what was it, XB multiplied by YC. Resultant of B is equal to XAYB XBYD XAYP plus XBY XBYD. Resultant of C is equal to XCYA XDYC XC multiplied by YA plus XD multiplied by YC. Finally, resultant dot D is equal to XC multiplied by YB XD multiplied by YB plus XD multiplied by YD. Alright. Fine. This is it. Now we need to return result. This is the multiply function of matrix exponentiation. Coming to the Fibonacci calculation. Okay, coming to the Fibonacci calculation. Fibonacci calculation, as I have told you earlier, let's call it Fibonacci, or else let's first do matrix exponentiation. Call this base and call this power, or let's call it n. Comfortable to write. Fine. Matrix base and a power n. Alright. Once again, we know matrix exponentiation is associative in nature. So while n greater than 0, if n is odd, what you do? First, let's take a result matrix. Let's take it RES. Okay, let's as you know, in binary exponentiation we took result 1. Now we need to take a unit matrix, right? We'll be multiplying some stuff to it, so it should be a unit matrix. How does a unit matrix look like? A equal to 1, B equal to 0, C equal to 0, D equal to 1. That's it, right? Yeah, that's it. Now If this is odd, in that case, result is equal to multiply result and base. Okay. Otherwise, base equal to multiply base with base, and n is equal to n right shift 1, or else n equal to n divided by 2. Both are same. Now return the matrix. What was it? Name of the matrix? RES. Yeah. So this is what you call matrix exponentiation. This whole code, right from struct matrix to here, this whole code is known as matrix exponentiation. Now, so far we are done with only matrix exponentiation. Now we need to calculate Fibonacci also. Okay. Let's say you want to calculate some Fibonacci of n. Okay, the matrix Fibonacci, what was it? I just told you 1110, right? 1110 here, 1110. Matrix, let's call it Fibo, or let's call it Fib, is equal to 1110. The magical Fibonacci matrix. Okay, we have this magical matrix and we need to exponentiate it to n minus 1, right? To find Fibonacci of n, we need to exponentiate it into Fibonacci of n minus 1. So let's write Fib equal to matrix exponentiation of Fib n minus 1. Once this is done, which would store the value of Fibonacci of n? Which would store the value of Fibonacci of n? This would, Fibonacci of a. So let's do Fibonacci of a. Let's test this out. Okay, let's write sign main return 0, or else let's print the Fibonacci series. That would be even better. Let's say Fibonacci till some 10 is enough to prove just this code works. Fibonacci of I. Done. Let's remove the input. Let's clear the output. And it should print the first 10 Fibonacci if and only if this is greater than. Yeah, it is. Fine. Let's run this. Looks like we got an error. Bit standard C++ dot h. Okay, so magically bits file got erased. No, I got a typo here. It's std, not st. Once again an error. Expected before while. Who keeps a comma before while? Okay, we have a declaration we need to. Okay, so it does print the Fibonacci series, but it prints 1. So yeah, I forgot to tell you, if it's 0, we need to directly return 0. Sorry, not here, I guess. Wrong function. The Fibonacci function. Now it should be printing the right stuff. Yeah. 0, 1. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. And this is the Fibonacci series, obviously. So we have done this using, since we have done this using binary exponentiation, this whole matrix exponentiation would take O of log n. And this multiply function, since we are doing it only for 4, it's O of 1 itself. O of 4 is O of 1. And space, we are just using a few kind of 1D arrays, so it would be O of n itself, or else I should say O of 4, so it's constant space also. So we have done the most optimal implementation of Fibonacci series with binary exponentiation. So this was all about binary exponentiation, guys. In this video, we have discussed simple binary exponentiation. We have also discussed modular exponentiation. We have also discussed apply a permutation k times. We have also discussed something known as matrix exponentiation. We have also discussed how to calculate Fibonacci in O of log n. And also you can apply it to almost any associative function if you are asked to calculate f power k, which means the function f applied k times. If you are ever asked to calculate this, always use binary exponentiation. Alright, so like, share, and subscribe to bring my aura back, which I lost after uh, writing this as less than twice. So thank you everyone.